As discussed in the Electromagnetic Brain video series, current research in neuroelectromagnetics is primarily focused on source reconstruction from EEG and MEG signals. In separate videos, we provided an overview of direct and inverse problem-solving methods for reconstructing these sources. If you haven't watched those videos, I recommend starting with the Electromagnetic Brain playlist before proceeding with this series. In this new series, we will explore the challenges and limitations of reconstructing neuronal sources from EEG and MEG signals, followed by an in-depth examination of advanced methods in neuroelectromagnetics. In the next video, we will take a closer look at problem space modeling, covering it in more detail. Following that, we will delve into source modeling, discussing it comprehensively and introducing relevant research papers in the field. Additionally, we will introduce and thoroughly examine the full-wave solution approach to solving the neuroelectromagnetic problem across the entire brain, using the corticothalamic system as an example. Finally, we will explore the concept of endogenous brain electromagnetic fields. Throughout these videos, we will address the key weaknesses in modeling and solving direct problems, categorizing them into three main areas: problem space modeling, source modeling, and electromagnetic solvers. To illustrate this, the basic models will be shown on the left side of the slide, while the advanced techniques will be introduced on the right. As we discussed in previous videos, modeling the problem space begins with segmenting MRI images and creating a mesh from these segments. These models, as depicted on the slide, typically start with a basic representation of the main tissues, such as the scalp, skull, and brain. However, it's important to note that these basic models significantly differ from the actual anatomy of the human head. On the left side of the slide, you can see these foundational models, while on the right side, more advanced models, introduced in recent studies, are presented. These advanced models take into account complexities such as the heterogeneity of the skull and white matter, the impact of flow of cerebrospinal fluid, CSF, the cerebrovascular effects, and even the intricate structures on the cortex with varying thicknesses, which also consider different arrangements of neuronal layers. Incorporating these factors allows for the creation of a more sophisticated model that more accurately represents the neural electromagnetic source reconstruction space. These advanced modeling techniques will be discussed in detail in the upcoming videos. Let's delve into the differences between actual neural models and those used in research. Traditionally, neurons are modeled as equivalent current dipoles, a simplification that serves well for many applications. However, when we require more precision, especially in understanding individual neuron dynamics, we turn to advanced models like the Hodgkin-Huxley model, which simulates the ionic currents and action potential generation in detail. On a larger scale, we use the neural mass model, NMM, which captures the collective behavior of neuron populations. This model is particularly useful for simulating brain activity as observed in EEG or MEG signals, focusing on the overall synaptic interactions and how different neural populations communicate. In cutting-edge research, we also encounter the neural nanometric model, which pushes the boundaries by modeling neurons at the molecular level. Here, each sodium-potassium pump, crucial for maintaining the neuron's electrochemical gradient, is not treated as a single unit but rather as a collection of multiple sources. This allows for an intricate understanding of the ionic exchanges and molecular processes that govern neuronal function. This level of detail is invaluable for exploring new frontiers in neuromedicine, where such precise models can lead to breakthroughs in understanding and treating neurological disorders. In neuroelectromagnetics, due to the low frequencies of brain signals, the static forms of Maxwell's equations are typically used, specifically electrostatic and magnetostatic models. These models involve solving the Poisson equations derived from Maxwell's equations under static conditions, usually employing methods such as the finite element method, FEM, or boundary value problem, BVP, approaches, which have been discussed in previous videos. A simplified version of these assumptions is shown on the left side of the slide. However, recent research has proposed significant improvements to this approach. One such method involves solving the full-wave Maxwell's equations for neuronal sources using the 3D finite difference time domain, FDTD, method. Initially, a full-wave electromagnetic model is applied at high frequencies, and then high-to-low frequency converters are used to adapt the electrical parameters of the problem space, such as tissue conductivity, to lower frequencies. This allows for an estimation of the neuronal field distribution within the brain. On this slide, images of the proposed models are displayed, and these topics will be discussed in detail in the video dedicated to the mathematical framework of neuroelectromagnetics in this playlist. In this slide, we transition from computational methods used to extract neuronal sources to exploring how these findings contribute to modeling consciousness through electromagnetic fields. The electromagnetic brain concept, which has gained recent attention, suggests that consciousness is linked to endogenous electromagnetic fields generated by neuronal activity. Studies, such as Galinsky's, demonstrate the presence of waves in the cortex that play a key role in these fields, with corticothalamic pathways and deep brain neurons, particularly in the thalamus, being central to this process. Building on this, an inhomogeneous anisotropic model of the brain cortex predicts the emergence of weakly damped wave-like modes in the cortical layers. These modes, which challenge traditional views of signal propagation, have been confirmed through numerical simulations, showing prolonged activity that doesn't correlate with neural fiber directions. This aligns with experimental studies revealing electrostatic field activity in the form of traveling waves, sometimes observed even without direct neuronal connections. Furthermore, nonlinear coupling between multiple wave modes can produce both high-frequency spiking activity and low-frequency rhythms, offering new insights into the dynamics of brain waves. These findings have significant implications for neuroimaging techniques like EEG and MEG, which detect electromagnetic activity and contribute to our understanding of memory and consciousness. In parallel, electromagnetic field (EMF) theory suggests that consciousness arises from dynamic electromagnetic fields generated by neuronal currents. These fields form a three-dimensional energy cloud around the brain, detectable as complex EEG and MEG patterns. Recent advances in nonlinear dynamic analysis of EEGs allow us to visualize these patterns in 3D, correlating them with levels of consciousness in humans and animals. While these findings support EMF theories, they represent only a fraction of the complexity and power of our brain's electromagnetic activity. To conclude, it's important to highlight a compelling theory regarding the origins of the brain's endogenous electromagnetic (EM) field and its potential role in consciousness, as explored by Hales, 2014. This work addresses the long-standing challenge of linking EM phenomena to consciousness by proposing a biophysically realistic mechanism. It suggests that the coherent action of transmembrane ion channel currents, which generate electric and magnetic fields, may be the primary source of the brain's EM field. These ion channels function like tiny current filaments, creating structured, focused fields that can influence nearby neurons, akin to a sweeping lighthouse beam. This mechanism not only provides insight into the origins of EEG and MEG signals but also suggests a new way to understand the subjective nature of perception. By positing a decomposition of the EM field that reveals both objective and subjective perspectives, Hales offers a physically plausible explanation for how these fields might give rise to the experience of consciousness, addressing some aspects of the hard problem of consciousness.